Hello everyone, I am Sonali Mate and I welcome you all for the session of Dynamics of Machinery, the subject of last year mechanical engineering. So in my previous videos, we have talked about unit number 1, that is on single degree of freedom system free vibrations. Now here, today we'll start with the discussion on unit number 2, that is single degree of freedom system forced vibration. So under this unit or under this video, our first topic of discussion is forced vibration and its elements. So the learning outcomes of this video are that the students will be able to understand the elements in forced vibration system. Also, they'll be able to understand the equation of motion of forced vibration. So let's have some examples of forced vibration. So here are some examples like pumps, motors, fans, cars, train bells. So these are the examples where we can see the forced vibration. Now basically what is forced vibration? As we have discussed in previous videos, these are the vibrations which occurs under the influence of external periodic force. Now here are some examples in which we can see forced vibration. Now pumps, motors, fans, these all are designed very carefully and also manufactured very carefully by meeting the standards value. But at the same time, there are some amount of manufacturing error. We are providing some tolerances, due to that some amount of unbalance is generated in the system, and as we know that unbalanced force is nothing but the cause of vibration. So this is one of the causes of forced vibration. Again, at the same time, non-homogeneous material. When we are using a system for a long period, so slowly the amount of friction in between the two parts goes on increasing and some amount of wear is there. And due to this, there is some amount of unbalanced mass which leads to unbalanced force. So this how the vibrations are generated in the system. So this generated vibrations are nothing but the forced vibration. At the same time, here you can see that this system is okay. If suppose your system is okay, but it is what we can say, it is going from the road which is rough one. So here you can say the base of the system is excited. So now this excitation force is due to this base on this car. So this is one type of forced vibration. Now the excitation of the system due to this forced vibration becomes harmful when it reaches at its resonance condition. So resonance is nothing but matching of two frequency, excitation frequency and natural frequency. So in order to make our system more safe, we have to design our system in such a way that the forced vibrations are damped. So for that we are using some amount of dampers. So here are some types of forced vibration. So first is forced excitation. So this is the system as we have discussed previously: spring, mass, damper and excitation force. Now here the excitation to this system is due to the external excitation force. So such type is called as forced excitation. Now second is base excitation. So the example of this is car on a rough road. So if suppose spring, mass and damper, this is nothing but your car which is passing from the rough road. So when this car is passing from the rough road, the excitation force is generated from the base and hence the system vibrates. So such type of vibrations, again it comes under forced vibration due to base excitation. Then again, if suppose this is your mass, spring and damper, but now in mass there is another small mass which is at eccentricity. Here you can see E, and here ME is nothing but the another mass which is lying at the eccentricity. So now what happens when such system is in motion? This system will rotate, this mass will rotate and it will generate an unbalanced force on this mass, and this will lead to vibrate the system. This will take the mass away from the main position. So again this is one type of forced vibration which is due to eccentric excitation. Now same eccentric base excitation means instead of eccentricity in mass, there is eccentricity in base. So if suppose this is the base and at the base another unbalanced mass is there, So due to that base excite, and this excitations are passed to the mass M. So the example of this eccentric excitation is you can say road roller, in which the unbalanced mass is attached so that the roller will vibrate. So the example of eccentric base excitation is shakers, mechanical shakers, which are used to find out the natural frequency of any system. What is this? We will come to know in our 5th unit. Okay. So now let's talk about force damped vibration with constant harmonic excitation force. Now always remember that forced vibration cannot be without damper. Why? Because if the forced vibrations are without dampers, then in every cycle the amount of vibration will go on increasing, and this will tends to reach the resonant frequency, and if the system achieves the resonance frequency, then it will collapse. In order to avoid the system to reach up to its resonance condition, so there is always need of damper. Hence forced vibration cannot be without damper. So there is always need of damper in order to reduce the vibration in every cycle, or reduce the amplitude in every cycle. So let's go through what is force damped vibration with constant harmonic excitation. So here we have seen about the elements of forced vibration. First is spring, which is having stiffness K. Another is damper. The damping coefficient, that is denoted by C. Next is mass M, and then it is external force. Now external excitation force, as we are saying, it is harmonic, so it is given by F0 sin omega t, where F0 is the magnitude of external exciting harmonic force, which is in Newton, where omega is circular natural frequency of external excitation, and t is nothing but the time. So the external excitation force is given by F0 sin omega t. So here is the system of forced vibration. So this much is your system. A spring with stiffness K, damper with damping coefficient as C, mass with small m. This is your excitation force F0 sin omega t. Now this is the mean position of the system. So this diagram is equilibrium position of the system. Now when the external excitation force is acted upon the system, and due to this excitation, system moves away from the mean position, so it is displaced by displacement x after the time t. So this is the extreme position of mass m. So this diagram shows you the displaced position. Now here spring gets elongated and also damper works. Now here what happens actually, if we have to draw the FBD, we have to consider the force due to spring, force due to damper, excitation force, and also the inertia force acting on this mass. Now we know that the spring is elastic in nature, so it will act, or it will generate some restoring force on this mass m, opposite to the motion. So your motion is in downward direction, so kx will be in upward direction. At the same time, damper is used to resist the motion of the mass. So damping force, it is given by Cx dot, it will be in upward direction. Also inertia forces acting on the mass, they are always opposite to the acceleration or opposite to the motion. So you can say mx dot is in upward direction. Now in downward direction there is excitation force, it is harmonic in nature, so F0 sin omega t. Now let's see how to form an equation. So according to D'Alembert principle, summation of inertia forces plus external forces is equals to 0. D'Alembert principle is nothing but any dynamic body can be converted into static body by applying inertia forces in the system. So from that actually this equation is formed. So summation of inertia force. So what is inertia force over here? Mx double dot plus external forces. Now what are the external forces? This is one force, second force, and this will be a third force. So all these three will come under external forces. So your equation becomes mx double dot plus cx dot. As all the three are in the same direction, So we are considering them as a positive. Mx double dot plus Cx dot plus Kx, and this is in downward direction. So minus F0 sine omega t. This is equals to 0. So this can be written as Mx double dot plus Cx dot plus Kx equals to F0 sine omega t. So this is nothing but the equation of motion for forced damped vibration. So I hope you have understood. For any queries, you can contact me on this email ID, and if you have liked video, then kindly like, share and subscribe it. In my upcoming videos, we'll be discussing on the solution of forced vibration. Thank you.